In this webinar, I will present you the latest features of version 25.0.0 in the field of SPH. Here we have an overview of the topics that will be discussed during the session. Given the challenges users face in manually setting the appropriate time step in SPH Solver, we have implemented an automated adjustment feature. This feature automatically defines the time step based on the velocity of the particles and bodies. Additionally, we have introduced the capability to attach an inlet source to a rigid body, thereby simplifying the definition of the inlet's path. Let us see this implementation in ANSA. First of all, we can see that in version 25.0.0 the SPH is a separate ribbon under the analysis category. All required functions for the model setup are gathered here. In the first group, all supported entities for the rigid body simulation are gathered, then some auxiliary tools are available for points and primitive shapes creation. All the available functions that can be used to generate particle sets are located in the particle set definition group. Lastly, the old SPH simulation window can be activated from the fluid simulation function. We switch to the Simulation tab where the time step can be set. Please observe that modifying the particle size results to recalculation of the suggested time step. Additionally, the Adaptive time step is available, allowing the dynamic adjustment of the time step during the simulation. Let us press Simulate and deactivate the geometry visibility. In the Extra Draw Info, we can check the current time step values. Let's move on to the Movable Inlet feature. In previous versions, when defining an inlet using nodes of moving body, the inlet would remain at its initial position during the whole simulation, as we see now. In order to overcome this issue, we can now attach the source to the moving body. This has been implemented by adding an extra Attached to column in the Particle Sources section of the Input tab, where the rigid body ID is specified. Simulating again, we see that now the source is also moving. Another feature that has been added is the possibility of defining the fluid viscosity using an expression. This is done from the Parameters tab. When selecting a custom fluid, the expression builder becomes available in order to set a fluid with dynamic viscosity. For example, we can use a logarithmic expression and then use the expression plot to visualize it. ANSA version 25.0.0 introduces fluid sensors, enabling the acquisition of detailed information such as the velocity, force, current wet area, accumulated wet area, and wetting time on a body, among other critical parameters. The sensors are hosted in a separate tab in the SPH simulation window. They are grouped in three categories: point sensors, which can be velocity, force, or wetting sensors; mesh sensors, which can be wetting accumulated, wetting current, total force or total torque sensor; and other sensors where we currently have the track center of gravity of fluid sensor. Point sensors are defined using a set of grids, where mesh sensors are defined using a selected rigid body. The pull-down menu can be used to change a sensor's type at any time. Only the active sensors are calculated. We can also regulate the number of generated sensor results per second. A new function, Point Select, can be used to facilitate the creation of a set of grids. A new grid is generated for each selected position and added in the specified set. Let's press Simulate to generate the results. When the total simulation time is reached or when Stop is pressed, a new entry is created both in the Sensors tab and in the database browser. Double-clicking on the sensor results, the Sensor Results Viewer is activated. The same can be achieved from the database browser from SPH Category Sensor Results List and from the context menu select SPH Results Viewer. On the right we have a label for each active sensor. For point sensor specifically, the different results according to the grids that the selected set contained are listed. We can plot the magnitude and any of the selected X, Y, or Z components. The exact values of the lastly selected result are displayed on the left. Another improvement of version 25.0.0 concerns the volume filling tool, which has undergone significant enhancements, both in terms of its filling algorithm and user experience. The user interface has been redesigned to enhance performance and usability. The volume fill is a separate function now outside of the SPH simulation window. In the first page, we select all faces that constitute the volume to be filled. The selected entities are highlighted in blue. In the Parameters page we specify the desired particle radius, and we specify the seed point, which will be at the COG of all selected points. The Particle Alignment Direction option indicates the direction where the particles will be stacked. The bounding box of the selected entities is depicted. By activating the Edit Generation Bounds, we can manually specify the length of the bound box in each direction. By default, the bound box is the minimum box that contains all the selected entities. In the Preview page, the filling level can be given either by setting the filling height, measured towards the selected particle alignment direction in the Parameter Selection tab, or by giving the desired volume of fluid. The tool fills a primary subvolume with particles up to the prescribed height or volume. The particles are visualized with a blue gradient. Additionally, by activating the secondary set option, an extra secondary subvolume filled with particles is created. This volume is defined as the complement volume previewed with a gray gradient. Upon finish, the two sets are created and their name includes the particle radius that has been used. Moving to the next implementation, the SPH solver is now fully compatible with Python, allowing users to utilize the full potential of the automation offered by Python libraries. In this example, the particle radius is set to 1.5 mm and there is no defined results output file. A new module is available to host all SPH-related functions. So here we can see a small script that calls the SPH solver entity, prints the defined parameters, and then updates some of them with new values and finally run the simulation and stores the results in the defined directory. So let's run the script. We can see here the old parameters that are printed and then the updated ones. The simulation is still running. When it finishes, the results are already loaded and we can animate them. With this, I conclude my presentation regarding the new features in the field of SPH. Thank you for watching.